Okay, so the lesson I'm going to be teaching today is open-end air columns. The goal is for you to understand how waves act in open-end air columns and the formulas associated with them. So an open-end air column is a tube that is open at both ends. There's antinodes and nodes. These would be the nodes, and this would be where the antinodes are. So the nodes are points of no displacement, which is destructive interference, and the antinodes are points of maximum displacement, which is called a constructive interference. And the fundamental frequency is the lowest frequency of vibration of a standing wave. So let's go through these harmonics. So, because it's one harmonic, n equals 1, which means one node. The second harmonic, n equals 2, so 2 nodes. And for the third harmonic, n equals 3, so 3 nodes. And the nodes on the second harmonic would be here, and the antinodes would be on both ends. And the node on this one would be here, and the antinodes would be on the end as well. An example of an open-end air column is a flute. A clarinet is like a closed-end air column because one side is closed and one side is open, and for the flute, both sides are open. Just so you can visualize the difference. As waves travel through a medium, it'll bounce back when it reaches the end, which causes nodes and antinodes. One node is called the fundamental frequency, which would be right here. The formulas are for fundamental frequency would be L equals 1/2 lambda 1, which L is the length of the pipe and the lambda is the wavelength. For higher harmonics, the formula is L equals n divided by 2 lambda n, where n is the number of nodes. And then the second formula to find frequency would be Fn equals n times F1 to find the frequency, where F1 is the fundamental frequency.
Anyone know how an open pipe or a closed pipe affects the pitch?
You know, fool know. Tell us, Mr. Audio. Consider a flute and a clarinet, two woodwind instruments that have a similar length and a similar diameter bore. One is a closed pipe and one is an open pipe. People seeing that a flute has a capped end would probably think it's a closed pipe, and that a clarinet with two open ends would act as an open pipe. However, the exact opposite is true. Here's why. Even though a flute has one end capped, it uses what's known as an air reed. In other words, the player blows across the hole near one end. Air can freely move in and out of this end, so it's actually an open pipe. A clarinet has a single reed on one end, but since the player effectively seals the end with their mouth, air can only move in and not out, so it's actually a closed pipe. Because the air in a closed pipe instrument has to travel twice as far to produce a sound, the pitch is an octave lower than an open pipe instrument of similar size and bore. That's why the lowest note on a clarinet, a concert D, is almost a full octave lower than a flute's lowest note, a concert C. Most single and double reed woodwinds have register keys that are located near the reed end. When this key is open, the closed pipe transforms to an open pipe, which produces a higher pitch.
Thanks, Mr. Audio.
Determine the frequency of the third harmonic for an open-end air column whose first harmonic frequency is 528 Hz. So first you're finding the third harmonic, which would be n equals 3. N stands for whichever harmonic you're finding. And then it gives you the first harmonic, which would be 528, so it would be F1 equals 528 Hertz. And then the formula you're going to be using is the frequency formula, which would be Fn equals n times F1. So the frequency at the third harmonic is the number of nodes times the fundamental frequency. So then all you're going to do is plug in the numbers into the formula. So it would be F3 equals 3 times 528 and you'd plug that into your calculator, and you would get 1,584. So your answer is 1,584 hertz. So for this one, you're going to be determining the frequency of the fourth harmonic for an open-end air column whose third harmonic is 200 hertz. So n equals 3 because they gave you the third harmonic, so n equals 3. And then f3 equals 200 hertz. It tells you that right here. So it would be f3 equals 200 hertz. And then you're going to set this up as a ratio, which would be f4 over 4, because this is what you're trying to find. And then you would equal that to f3 over 3. You're going to solve for f4 by multiplying both sides by f4. So you'd multiply by 4 on both sides, which would give you f4 equals 4 over 3 times f3. And then f3 is equal to 200, so that would be f4 equals 4 over 3 times 200, which you would plug into your calculator, and you would get 266.67 hertz. And that would be your answer. So for this one, you're going to be determining the wavelength of the first harmonic wave pattern for a 40 centimeter long open-end air column. So your formula for this one would be L equals 1/2 lambda 1 because you're finding the wavelength. But you have to find the wavelength, so you have to rearrange it to find lambda 1. So you would do that by multiplying both sides by 2. And in case this isn't clear, lambda 1 stands for wavelength. So once you multiply both sides by 2, you're left with 2L equals lambda 1. So from here, you would just go straight into plugging in your numbers. So that would be 2 times 40, which equals 80 centimeters. So the wavelength for lambda 1 equals 80 centimeters. So for this problem, you're going to be determining the wavelength of the fourth harmonic wave pattern for a 2-meter long open-end air column. So n equals 4 because it's the fourth harmonic, and L equals 2 meters because it's 2 meters long. And then the formula you're going to be using is L equals n over 2 lambda n. And you have to rearrange it to solve for the wavelength, so you're going to do that by multiplying both sides by 2. And when you multiply both sides by 2, you're left with 2L equals n times lambda n. And then you have to divide both sides by n to get lambda n by itself. So you get lambda n equals 2L over n. And then you're going to go ahead and plug in your numbers. So it would be 2 times 2 over 4, which gives you 4 over 4, which is equal to 1 meter. Here are 2 example problems. If you want to try them on your own, you can pause the video, and I will post the answers on the next video if you want to check your answers. Here's the answer to the first one, and you can pause it if you want to check your answers with this. And here's the answers to the second one. You can also pause it if you want to check your answers. So by now you should understand how waves act in an open-end air column and the formulas associated with them. You should also know that an open-end air column is a tube that is open at both ends, that there's antinodes and nodes, that the nodes are points of no displacement, which is a destructive interference, and the antinodes are points of maximum displacement, which is called a constructive interference. The fundamental frequency is the lowest frequency of vibration of a standing wave. You should know that an example of an open-end air column is a flute, and a clarinet is like a closed-end air column. As waves travel through a medium, it'll bounce back when it reaches the end, which causes nodes and antinodes. One node is called the fundamental frequency. And you should also know how to determine frequencies of harmonics for open-end air columns and what formula goes with it. And you should also know how to determine the wavelength of harmonics for open-end air columns and which formula is associated with it. And you can pause the video if you want to reread all of this and see the formulas one more time.